device, if you will, that basically can generate these things for waste material. I'd like to acknowledge the co-authors and a number of students in my lab. We have a lot of fun working on this project. And this is a picture of my son and his buddy, Mikey. And I thought this t-shirt was extremely relevant to this conference. Either we're lowering expectations for our kids these days, or Mikey knows something that the rest of us, the rest of the general population doesn't. But I think it's going somewhere that poop can really become a great resource. And last fall, the Japanese toilet manufacturer Toto announced that they have developed the first human-powered motorcycle, if you will, that can travel across Japan. And this driver looks like he's about to make a deposit to power the vehicle. Now, is this really true? I'll get to that later. Okay, so we recognize that wastewater or waste material is really should be viewed as a renewable material, and there's a paradigm shift that's undergoing, recognizing that we can harvest waste and turn that into water, energy, and nutrients. We found this in a really old wastewater treatment textbook, and it says it's true there are resources in sewage, but like the extraction of gold from seawater is very costly, and it's not worth it. But we'd like to challenge that assumption again, and being that there's different technologies and the world's different these days. So I think for us to achieve the Millennium Development Goals, especially related to the targets on sanitation, we need to develop different technologies, as many of us are talking about here at this conference. And here are a number of properties I think that really need to be embedded in these technologies. But probably the first one, and that's what the Gates Foundation and many other organizations realize, is that we really need to focus on recovery rather than just removal, and turn, recognize the value that's embedded in the waste material. So here's sort of our process in the box. What we envision is a one-step device that can turn mixed waste, basically, whether you have poor flush or a variety of sources, you have food waste, other things mixed in, but really mixed waste from different sources. And through anaerobic digestion, you can recover biogas, but the difference is that we're going to apply membrane separation on this process. And this, I think, will be a key parameter for the process. Okay, so let's go back to the carbon cycle. And this is something that we learned very early on, but unfortunately, a lot of people forget. So basically, carbon goes around and around the Earth, is mediated by microorganisms, is biogeochemical cycling. And the fact is, what we consider waste is really food for a variety of microorganisms. So in nature, there's really no such thing as waste. It's all food and energy source for organisms. So waste organic matter is equal to reservoirs of energy. So this parameter that we're familiar with, chemical oxygen demand, really the more polluted, the higher the COD, the more energy there is within waste material. Okay, so if we look at this world of carbon, right, and I'd like to look at methane being the most reduced form of carbon possible, and carbon dioxide being the most oxidized form possible. You can view methane as very energetically rich, whereas carbon dioxide is completely devoid of energy. And the rest of us, the rest of the organic world, falls somewhere in between. And that could be biomass, the food we just ate for lunch, could be fecal sludge. They fall somewhere in between here. And you see that through anaerobic digestion, we can basically convert the biomass to methane. But then there's a natural oxidation process of respiration, and it gets converted to carbon dioxide again. But thankfully, there's a mechanism called photosynthesis, which basically converts this energetically useless carbon in the form of carbon dioxide back into useful carbon, and with the power of the sun. So this carbon cycle continues. I think this is really important for us to keep in mind as we're looking at technologies that can harness energy and resources. Okay. So there's this very popular bumper sticker or T-shirt that floated around in the 80s, right? And I like to think that after this happens, this also happens. And so really the bumper sticker could be modified to say methane happens. That's true. Methane happens, and in fact it starts to happen within our digestive tracts, and once it enters the environment, if it's anaerobic, it continues to happen. And anaerobic microorganisms are very efficient at converting organic matter into methane. And compared to aerobic organisms, they have very little cell yield, so they're very unselfish. They take a very low commission, if you will, to build biomass. They convert about 90% of the energy into methane. If we're looking at energy recovery on an electron basis, for every bit of biodegradable organic matter, we get all of the electrons back, eventually in the form of methane. So, when we're looking at technologies, anaerobic digestion, methane production is something that works well. There's a saying, if it ain't broke, don't fix it, right? So let's look at anaerobic digestion and say, well, what can we do to make that better? And in terms of the energy content of wastewater waste, municipal wastewater in the United States is relatively dilute, so the energy content is limited. However, fecal sludge with a high solids concentration would be a lot more energy rich. Of course, the more COD you have, the more energy embedded. And a variety of anaerobic wastewater treatment processes have been in existence for a long time, which you're familiar with. In India, there's a large public toilet, in fact, that converts human waste into biogas, and then biogas used for cooking, or lighting, or also electricity. So here's a good example of turning waste to energy via biogas. But what are the limitations of anaerobic digestion? Well, one of them, I think, is related to the reuse of the effluent from anaerobic processes. If you're relying on gravity settling, gravity separation, which many processes do, there's an inherent limitation that anything that's at density close to water, such as colloidal material, or microbes, or bacteria, or even helmet bags, could leave the system, and we can't capture those through gravity-driven separation systems and anaerobic digestion. So that puts a limit on what we can do to safely reuse the effluent from these systems. So how do we completely separate the colloids and liquids? One idea is to use membranes. Membranes are basically thin films that are basically providing an absolute barrier for the rejection of a variety of material. Depending on the pore size, we can reject different things. So here's the classic filtration spectrum. On top, you see different types of membrane classifications, all the way from screen and clog to microfiltration, ultrafiltration, now known as reverse osmosis. And then along with that, you get different rejections of material. You can see that, for example, in microfiltration is able to remove bacteria or even some cells, and then when you get down to the level of ultrafiltration, even viruses can be rejected. So this is important because many of the pathogens that we're concerned with fall within this range. Looking at it a little bit differently, this is basically the same information, but presented in terms of the different types of filtration, what they can reject. And the top one on the graph on the left shows microfiltration on top, and then ultra, nano, and then the reverse osmosis. Well, the average size of an helmet bag is about 35 microns, and that can be easily rejected by microfiltration. But beyond that, we can also reject bacteria and viruses. And one thing that's very interesting is also when membranes are put in use, the pore size sort of tightens, if you will, because of the covering of the membrane surface with biofilms. And that's a research area that's ongoing now. That we can get even additional removal with the membranes that's in operation. Here's an example of the membrane surface of the membrane that we're using. You can see that the pore size is images from the scanning electron microscope. Average pore size is 0.03 microns. You can look at the membrane surface with atomic force microscopy, showing the roughness on the membrane surface. And here's a cross-section of the membrane. You see on the very top, that's a separation layer. It's a very dense layer, and then the pore is going to open up. That's to allow water to go through once it makes its way through the top layer of the membrane. So membranes are very robust, very flexible systems. They're highly scalable. They provide this absolute barrier for the rejection of a variety of undesirable contaminants. So we can combine membrane with a bioreactor, a biological process, right? That's what we would call a membrane bioreactor. So what do you do with a membrane bioreactor? If you start with a CSTR, or a completely stir-type reactor, and this could be, for example, a sludge pit, fecal sludge pit. Whatever goes in, if it's complete mix, is what comes out. So there's very little differentiation or separation for contents. Of course, we can add a clarifier, a gravity-driven clarifier to that. We get some separation. But as I noted previously, that colloidal material will not be able to settle within such a system. But if we apply a membrane system, now we're going somewhere. We can get basically 100% removable solids. Not to mention that we now can create a wastewater treatment system that is very compact. For example, we can replace this entire wastewater treatment train with really a small one-step system. And there's a number of applications to the membrane bioreactor systems, MBRs. Some of the issues are related to energy and maintenance of these systems, and I'll get to that more in a minute. So where do you put the membrane? You can either put the membranes inside the reactor, and these are submerged configurations, or you can put them outside, external configuration. Right? Keep in mind what I've spoken so far about membrane bioreactors really are related to the aerobic systems. These are basically activated sludge systems adapted to using membranes. What we're interested in working on is an anaerobic membrane bioreactor. Okay, so membrane bioreactors have really penetrated the commercial marketplace. These are systems that are in commercial use. There are a variety of companies that provide these services. They're small systems. You can use them even inside buildings. Right? So there are a variety of green buildings that recycle the building's wastewater and convert that into reusable water within the building. We can even use these on ships, for example. There are cruise ships that use membrane bioreactors to turn all the wastewater into usable water. Right? So these are basically systems that are high performance, they're small scale, and can provide a high quality effluent that can be reused. And some of the top uses have been, for example, sewer mining, to mine water from sewers. Okay, so there's a lot of excitement around membrane bioreactors, and this one came from, I believe, 2003, and from the Water Biotechnology magazine. Right? And they're very excited about membrane bioreactors. Asked the question, can MBR solve the world's water crisis? And this is basically a summary of a meeting that happened with a number of wastewater experts. And they identified that MBRs have a lot of potential, and in blue, these are the benefits of MBRs highlighted. They provide really high quality effluent. There's reliability. It's a good use of land because they're compact, and they're very adaptable. They're small systems. But what are the issues that with MBRs? If we want to make these actually a solution in global water and sanitation fight, what are the issues with MBRs? Well, cost. These tend to be expensive systems, requiring a lot of components, a lot of you need a lot of know-how to run these things. There's a chemical cost to clean the membranes, energy cost to run the membrane system, the bioreactor system, and also there's just a general lack of familiarity with the system. Okay, so this has basically provided the motivation for the work in my research lab for about the last 8 to 10 years. Basically this table. Say, well, if MBRs have such a potential to help solve the world's water crisis, and are people really looking at these issues? But unfortunately, I think most of the marketplace has been going towards sort of the users who can afford MBR systems. And what has been sorely neglected is the sanitation market in developing countries. And there are really commercial vendors that are not targeting that sector. So I think that's a shame that we have such a wonderful technology, but it's not being applied to help solve global sanitation problems within developing country context. So what we envision is that we like to develop an anaerobic MBR system that's basically appropriate for resources. The reason we want to do this anaerobically is because for the energy reduction in an anaerobic system, and also for the energy recovery aspects. And so the trademark name we have applied to our system is the NEWgenerator, and we envision also that the NEWgenerator will be simple to operate, maintain low energy, adaptable to different settings. We can adapt to different energy sources that are available, or even be completely off the grid. And also the recover material resources can also be flexible depending on what the user needs. This is a laboratory system that we have constructed and tested, and it's basically an anaerobic bioreactor coupled with a membrane separation system. Without going into all the details of the graphs, what I want to show you is that the membrane system coupled with the anaerobic process is able to achieve really high quality effluent in terms of carbon removal. We're able to get 98% COD removal in such a system. So it's a very efficient conversion into methane. And then what about the nutrients and phosphorus, right? So anybody who's familiar with anaerobic digestion knows that anaerobic digestion does not remove nutrients. In fact, so if your target is to discharge your effluent into a receiving wallet, you would not be doing anaerobic treatment. You would need to follow that with something else. But if your target is maybe conserving the nutrients, right, you want to leave that in the effluent, you want to maybe liberate it from organically bound, the nutrients are bound in solid material, however you want to overcome the pathogen issue. Then I think anaerobic MBRs can provide a very safe effluent for you to use. So in fact, we're able to recover 90+% of the nutrients that are bound up within the waste solid material in the system. And in terms of the turbidity or the clarity of the system, you can see the one on the left is the wastewater, simulated wastewater entering the system. The one in the middle is the sludge within the reactor. And then on the right is the effluent. It's very high quality, clear effluent that you can reuse for a variety of things. Okay, so this is what we envision, and we have a Gates Foundation grant, round 7 phase 1 grant, is basically to develop the system for the field. And so what we envision is, have our NEWgenerator recover the resources, and rather than get rid of nutrients, let's use the nutrients and the water together for agriculture, which is one of the large uses of water in the world anyway. And then the biogas that you can capture from the system can be used readily for purposes such as cooking and heating. And the nutrients that you recover, you can either use to grow crops. You can maybe precipitate straw from them, and so if you can't use it readily, you can package it as a solid fertilizer. Or the other thing you can do with it is to grow algae for biofuel. And there's a lot of interest in this topic now, and people recognize that there's a lot of synergy between algae and wastewater. And in order to grow algae sustainably, we really need to grow on wastewater, because it doesn't make sense for us to pump groundwater and add bags of fertilizer to it. So there's great synergy between the two. In fact, that's one way we can extend the usefulness of the nutrients that's in the wastewater, and basically add additional carbon back in from the atmosphere. If you come back to this picture, algae allows us to take useless carbon dioxide and turn it into new energy sources. Some of this, we've looked at a variety of species in the lab. Some of the species are chlorella species. They work very well, and these are some examples of photobioreactors we built in the lab. We're coupling this project with a project from the National Science Foundation. Basically, is to look at the integration of algae in the wastewater treatment system. Okay, so this is what we envision for the NEWgenerator, resource recovery machine in a box. This would be what the system might look like. One of the things that we're doing is that we feel it's very necessary to combine research with education and practice. You can't do research in a vacuum. So to that extent, there's a lot of student involvement coupled with the local K-6 school. And basically, we're pilot testing the NEWgenerator using the septic tank at the school. And what we have developed at the school in combination with 2 other projects, the NSF project and also the food waste project, is a station that we call the Biorecycling, Bioenergy Research and Training Station, BRATS. Right? And these are some of the students who are working on the project. And here's some rendering of BRATS. So basically, we have a NEWgenerator station, fertilizer reuse, algae photobioreactors, just taking different angle views of the system, food waste digester. So really a complete demonstration of biorecycling and coupling this into curriculum. So we're able to basically work with the 6th graders and try to get them to really think about that diagram I showed, the carbon implements. And they spend a whole month working with anaerobic digestion, algae, and composting systems. And here's some pictures of the kids really getting hands-on, getting dirty, building their own biodigesters from soda bottles. what we want to do is really change how they look at waste, change how they look at carbon, and think about this issue that it's really not a waste issue, it's a carbon and nutrient mismanagement issue. And so the last thing I want to end with is, so we saw this slide yesterday from Dr. Cohn about sanitation value chain. So, where would a new generator possibly fit in? One is, for example, the Faecal sludge pits. Right? We heard a lot of talks about the pits filling up in no time and causing a lot of problems. Well, what if you can couple this with a safe dewatering device, such as a NEWgenerator, and you can basically dewater the system, and you can harvest the water and with the nutrients in there in a safe manner, and then do local reuse, for growing crops or other things. That can basically stretch out the useful time for the sludge pit. Now, once the contents have been emptied and conveyed to a resource recovery facility, a larger scale NEWgenerator could be implemented there, basically to do larger scale recovery. Right, so with a membrane system that's flexible, it's adaptable, scalable, so there's enough technology partners to complement our process and basically create synergy from this. We're also looking for implementation partners to field test our system. And so if you're interested or just basically want to have a bit better understanding of the system, I'd love to talk to you. Okay, so coming back to this picture, it turned out to be a publicity stunt. It wasn't really human waste in the toilet, but basically this is a biogas motorcycle with a toilet tank installed. But it does basically raise a lot of interest and conversation about that you can effectively use biogas for a variety of things. But maybe in a not too distant future, we could have a system like this, where it actually in real time gets converted to energy, so you can have off-the-grid toilets, sort of like what the foundation is envisioning with the reinventing a toilet. So here's my contact information.